Okay, so in this lecture, we are going to see linked state routing protocol, and we will do some questions based on the distance routing protocol also. Okay, so let me just recall you that what was the distance routing protocol and all. So basically, in this particular network layer, we are going to see few of the protocols which are related to routing protocol, maybe DVR, LSR like this. And basically these consult with the routing table, and we are also going to see some of the protocol, IP protocol, ICMP protocol, these kind of protocols. Okay, so this DVR protocol I have already covered, but let me just quickly tell you that suppose that you are at U and you want to go to, let's suppose, at this V. Now you need to decide like which is the shortest path. Either you should be going via X1 or maybe via X4. Let's suppose there are two paths, right? So that's what you need to decide. Now, distance vector routing says that suppose this is your topology, then what you will do, you will advertise locally, which means you will say that this A is going to advertise to B and to E also, right? So which means A will say A will share its vector with B and E. B will share its vector with A and E and C also, right? So these like all of the nodes share their vectors with the neighbors. That's what happens in the distance vector routing protocol. So suppose if you are at here, yes, if you are at J, then at J you will say that the vectors that you will be receiving are from A, I, H, K. A because A is a neighbor, I because I is a neighbor, H because H is a neighbor, and K because K is a neighbor. So you will be receiving vectors from this. And now how to calculate the new vector? What you will do, you will first add the cost, which is J to I, which is 10. So you will add this cost 10 here. And then you will take the minimum, right? You will add the cost from J to A, J to I, J to H, and J to K. And then you will take the minimum among all. And this entry, which is J to J, always 0. So that's how you are going to calculate this vector. And that's what we did, right? Okay. So this flowchart is saying that you will wait for any change in link or message from the neighbor. So you are going to advertise only when there is, you are going to change the routing entry only when there is any change in the link or there's a message from the neighbor. So change in the link means what? Suppose that all of the sudden this link get break. Then also then this B will immediately change its entry to entry from A to B to A to B infinity, right? So it will say that now you cannot reach to A, something like that. I mean, you cannot reach at least directly, right? I mean, you may reach via C. That will depend if C also has some entry. Otherwise, we will immediately update that, okay, I cannot reach directly. So this is unreachable, which means it will say that, okay, it is infinity. Now, at later point in time, if B receives any vector from C, then it may update the value. Maybe C will say that C, I can reach maybe via this line. Then it will update its value later. But currently, it will just set it to infinity. So this is basically this is where I am. So basically I will be waiting for any change in the link or maybe any message from the neighbor. If there is any change in the link, then maybe link get disconnected, maybe cost get increased, or maybe cost get decreased, right? Then I will recompute my estimations, and then then I will notify to the neighbors also. If distance to any destination has changed, then I will notify to the neighbors also. So that's what keep on happening. Now we have taken one example. So suppose this is the example, and in this example, like I'm saying, the initial distance vector vectors are given, and then at A you will be receiving something like this, and at B you will be receiving something like this. So we can take the minimum and all, right? We have done this earlier. Okay. So now there is a problem that is called count to infinity problem. I mean, it is a problem just because you are going to take little more time in the distance vector routing protocol just to identify that, okay, this is unreachable. So basically, this problem says that if there is a good news, which means decrease in the cost, then it travel fast. Okay, good news travel fast. Bad news travel slow. Now, when I'm saying this is a problem, it doesn't mean that distance vector routing is not useful. It's a problem. It means that I can still bear with this problem. The only thing is that I cannot converge faster, which means if there is a bad news, if this is going to get disconnected, or maybe increase in the cost or something like this, if there is a bad news, then this B and C cannot reach A, right? So suppose if there is a bad news, then this B and C, okay, so maybe this slide only. So suppose there is a bad news, then this B and C cannot reach to this A, then they has to set it to infinity. Now this problem is saying that they will set to infinity, but it will take just little more time. That's the only thing, right? Otherwise that's okay. I mean, it is just going to take little more time, right? So that's the problem that we have seen earlier. Now there is a solution to this problem, which says that do not use this value. What I know, this roots come from you, which means that suppose, let me talk about the count to infinity problem. Okay. So this is saying that suppose initially you are having, this is A, this is B, this is C. Initially, suppose this is the cost. Okay. After some time, what happens that this A get disconnected, and let's suppose you are going to have something like this. Okay. So suppose that this is the link after some time, which means this is getting disconnected. Now, in this case, this B will say, like, okay, I'm just writing the cost to A. Okay, these are the cost to A. B will say that, see, I cannot reach to A. It seems like the A is disconnected. Now, C doesn't know that, okay, B has set it to infinity. C is still saying that earlier it was 2. So C is saying that I can reach to A using 2. Now, tell me, is this a any round, or you're just updating this C? Initially, it was just 1 and it was 2. And from this 1 and 2, the moment it get disconnected, right? The moment it get disconnected, at the same moment, this is 1 is changing to infinity. This is not any round or something, okay? Which means like you are going to change to infinity in no exchange. Immediately, you are going to change to infinity. Now, this is after next round. What's going to happen? You will say that, okay, this C will say that I can reach in 3. B will say, see, I can reach in infinity, which means 3 is better, right? And it will say that, okay, okay, take my infinity. But C will say, see, I have the better thing, which is 2. Okay, so why to take your infinity? Something like this, right? And then, yeah. So see here, what's going to happen? That, okay, tell me if this is infinity, this is 2. Now you are going to say that B is going to say that I can reach to A in infinity, and then C will say at the C, what you have, what you will be receiving. So okay, let me just write here. At B, what you will be receiving? At B, you will be receiving something from C, right? Which is 2. And at C, what you will be receiving? Only this infinity, right? Only this infinity. So C has no choice. It will make it to infinity, which means that at C, I'm only receiving from B. So it will say that, okay, infinity, then it will change it to infinity, right? But B will change it to 3. Is this okay to everyone? Now, what's going to happen? Now you are going to say in the next round, what you are going to say, that B will say that, okay, I can reach in 3, and C will say, see, I can reach in infinity. So maybe it will be just infinity, because at B you are just getting information from C, and at C you are getting information from B. Now if B can reach in 3, then C will be reaching in 4, right? Something like this, because C to B is 1. So you will keep on incrementing this number from 3 to 4, and then 4 to 5, maybe 5 infinity, something like this. And then ultimately this number will be some larger, right? Then it will be like, maybe let's suppose your maximum number is 15. Then you will set it to, I mean, the moment it is 15, you will say, okay, I think it is too large. That means that this will be keep on incrementing, and then you will declare that to unreachable mode, right? So that's why this is a problem, which means, like, at the end, what I wanted the moment it get disconnected, I wanted infinity, right? And that will happen. That's not the thing that will happen, but it will just happen very slowly, right? It will just happen very slow. Slow is a problem here. There is nothing wrong. It's slow, right? Count to infinity is not wrong. I mean, that's okay. It is not wrong. It is just slow, right? I hope that is okay to everyone. Now, so this was the problem. Now, what is the solution to count to infinity? As a solution, I'm saying, right? So as a solution of count to infinity, as a solution, what I'm saying, that what you do, if you're getting something from me, so see, this was the problem. Now, as a solution, I'm saying this, that if Okay, so like that is the situation that I have currently, right? This will be this is sorry, this is A, this is B. So that is the situation that I have currently. The moment it get disconnected, it will set it to infinity, right? Now this B will say that okay, let me just make it, I mean, let me just pass it over to C, and C will also pass it over to B. But if this is 2, and what is the next hope for the C? Next hope is B only, right? If that is from the B, then I will not pass. Okay, so I will not pass this entry. I will just say that okay, I cannot pass this entry, which means that maybe C will send the vector, which is something like this. Okay, maybe it will send the vector something like this. It will make this entry blank. And yes, B is not obviously from the C. I mean, if you are from me, so C is from B, then it is not going to advertise to B, because the reason is very simple. C cannot say to B that see, I can reach to A in cost 2 by U only, and now you update that to 3, right? That was the earlier problem. See, earlier I was just sending the cost. Oh, yeah. So earlier I was just sending the cost, right? I was just sending, okay, this is 2, this is infinity. But now I will send cost only when the next hope is not that node only. Okay, which means if I'm advertising to B, then whatever in whichever entry this next hope is B, I will not send that entry. I will just say that okay, it is blank. I don't know. It will C will say I don't know. Okay, and it will send infinity. So now tell me at B what you will be receiving, and at C what you will be receiving. At C you will be receiving infinity, so it will change it to infinity. But at B, what you will be receiving? You will be not receiving anything, right? So at B, you will be not receiving anything, so immediately it will change to infinity. So that's how you are solving the count infinity problem. And that is called, like, this is just a name, that is called split horizon solution. Okay, that is called split horizon. The solution name is called split horizon. What the solution is saying, that if this C, okay, if this C, the next hope is, okay, next hope is B, then do not advertise this, just make this blank. Okay, that's what the solution is saying. Just make this blank. This is a blank entry, or do not write anything, right? Blank, or don't send, or don't basically send. Okay, don't send this entry. This is a solution which is quite logical, and this is called split horizon. Let me know if there is any doubt here. Now what's going to happen? Now if you're not sending to B, then sometimes B don't know that why it is not sending. I mean, B may get confused. Maybe it is because split horizon, or it is because that this C is not receiving something from A. So basically, if you're not sending this entry, then we will get confused sometimes. Okay, this is a solution, but in this solution also there is some little improvement. I mean, instead of blank, you can also send infinity. Okay, instead of this blank, you can also send infinity. So instead of blank, we can also send, or what you can do, this 2B, if you have 2B, then there is one more improvement, that you can send infinity here. You say that okay, I don't know, like, I mean, I can reach in the infinity, something like this. Okay, so either you do this or you do this. There are two different solutions. You don't send, then it is called split horizon. You do this, then it is called split horizon plus position reverse, something called as position reverse. They are saying that C can still send the entry. In the split horizon, you are not sending the entry at all. Okay, or maybe just keep it blank, or maybe let's suppose that you're not sending at all. Don't set at all. This is a split horizon. In position reverse, I say I can still send, but let me make it infinity. So what is the benefit of this position reverse? The only benefit, or maybe the only logical thing that you can think of, is that if you are sending infinity, then at least we will get to know that okay, C is sending me something, right? If you do not send anything, then we will just think like, okay, I don't know why C is not sending. Maybe C itself is down, right? So maybe there's some problem with C. So that's what we will think. Okay, I hope you got it. Let me know if there is any doubt. So have you understood both the problems? Should I just show you the frozen screenshot? I mean, okay, let me just pull over the frozen. Let me just show you the frozen. Okay, just a second. Oh no, there was no sound. Okay, I have explained so many things. Okay, so let me quickly explain. So see, here there are two solutions. One is split horizon, one is called position reverse. Okay, so this split horizon is saying that do not send anything. Like so, here in this example, this is A, this is B. Now, split horizon will say this B will not send anything to A. Okay, so see here they are saying that B thinks that optimal route to access via A, so it does not advertise any piece of information. Okay, it does not advertise any piece of information, which means this B does not advertise anything to A. That's called split horizon. And what is position reverse? Position reverse will say that B can still advertise, but it will put the value infinity, right? So here, see, we can still advertise with a value for A, but it will keep the infinity. The value it will keep the infinity. That's the only difference. I hope you understood the difference, right? So that's the difference between split horizon and position reverse. Split horizon will say that do not send anything. Maybe let me just correct it. Okay, do not send anything. And position reverse will say you can send, but just keep it infinity. And why this position reverse is making little sense? Can anyone tell me quickly? Because if you're not sending anything, then this B will get confused that why C is not sending. Is this because of the split horizon strategy, or maybe because the C itself is down or something wrong with C, right? So that's why, since the B will get confused if you're not sending anything, then B will get confused. So that's why, just to keep this confusion away, okay, though C will say that okay, let me send it, just make it infinity. That's the only, these are just two terms. Okay, I mean either you don't send or you keep it infinity. Then these are the two terms. I hope you understood. Now, yeah, these are the solution. Now let's move to one new algorithm that is called linked state routing. But before that, let me just tell you one thing that currently it seems like that if you are using a split horizon or position reverse, then it solves all the problem of this count to infinity, right? Now, but there are now, like we have just shown you using the two nodes, but there are networks using the three nodes that you can make, and even the split horizon and the position reverse combined, you cannot solve those that problem. I mean, currently you are able to solve with the split horizon or position reverse, but if you are still having some networks in which you cannot solve that count infinity problem using these two also. Okay, so maybe some little more complex networks. So if there are three nodes or maybe more nodes, then this situation may arise. So can this split horizon or position reverse can solve all the this count infinity problem? Then answer is maybe in some cases it can solve, in some cases it cannot solve, right? So what is the solution? Permanent solution. There is something called path vector routing, which means it will send the complete path. Like you have the complete path that okay, after this what should be there, after this what should be there. Anyway, that is not in our syllabus, but there is something called path vector. That is a modified form of distance vector, and in that you can solve the problem completely, right? Okay, that's not in syllabus, so we will not go to that. Now let's just move to another routing algorithm, which is called linked state routing. So distance vector was used in ARPANET, which was the initial internet that we have. In 1979, we used to do this distance vector, but it has been replaced by linked state routing now. The primary problem was caused its demise that the algorithm often took too long to converge after a network topology changed. Okay, due to the count to infinity problem. Can you always solve this count to infinity problem? Tell me quickly. Can you always solve this count to infinity problem? Answer is no. In some cases, you can solve this using position reverse or split horizon, but in some cases you cannot solve. Okay, if there are three nodes, then maybe you cannot solve. Okay, if there are three nodes, then the two nodes instability can be avoided by split horizon combined with the position reverse. However, if the instability is between three nodes, then stability cannot be guaranteed. You cannot guarantee that you can always solve this problem. Okay, yeah, so now let's just see linked state routing, which is currently the more useful algorithm. But it is very easy algorithm. So suppose this is the topology that you have. A is connected to B, A is connected to E with these costs. Okay, these are the costs that we have. These are the costs. And now in this algorithm, what every router will do? Every router will flood the information not to just neighbors, to everyone, which means E will flood this information to D also, C also, B also, A also, and F also. So every router just flood this information to every other node. So what E knows, E says that okay, distance to A and distance to F I know, which is 5 and 8. That's what E knows, right? That's the vector at E. Now it will get propagated to every network, okay, every router. So this is what linked state routing says, that you are going to flood to every router. Now, what is how it is working is basically you are going to have some, let's suppose these are the vectors for every router, which means like for A, I have, for A knows about B and E. So A knows about B and E. B knows about A, C and F, right? A, C and F. B knows about A, C and F. So here I do have A, C and F. Now what are these two fields that I will just come in just a minute. Okay. So these two fields are not, I mean, at this point in time, these two fields are not very interesting to us. So let me just remove it. So basically, these are the vectors that you have. Okay. So these are the vectors that you have, which means that at A, okay, this is the vector at A. At A, since A knows about B and E, you will be having B and E. B knows about A, C and F, you will be having like that. Now, what A will do, A will take this vector and will broadcast to everyone or flood to everyone. Okay, which means it will just send it to the whole topology. So what is the benefit of that? Now, since A will be forwarding this packet to every other network, and A will be, or since every router is doing the same, then A and every other router will be receiving the packets from every router. So at A, if I talk about at A will be receiving the router, the vectors from E, B, C, D, and F. Earlier, they used to receive only from the neighbors, right? A used to receive only from B and only from E. But now at A, can you tell me how many vectors are there? At A, these all the vectors are there, right? I mean, you have the vector at A also. So basically at A, you have 1, 2, 3, 4, 5, 6 vectors, right? Yeah, you have all the vectors at A. So since you have all the vectors at A, it means you know the whole topology. Every router now knows the whole topology. Every router knows whole topology. Because if you know all of this, see this representation and the graph representation are same. At every router you have this representation, which means you have the graph representation. So these are called link state packets. So if you have all this information, then at every node you know what is going on. Like, I mean, you have the at A you have the whole graph, at B also you have the whole graph, at E also you have the whole graph. So what is the benefit of this? Now you will say that, okay, if you have the whole graphs, then what you can do, you can just apply the shortest path algorithm. So it means you can apply shortest path. So what is the better shortest path? If there is no negative edge, then you will be applying Dijkstra. Okay, you can apply the Dijkstra algorithm. So that's all. I mean, that is what you have. So basically at A, you can just converge just after one flood. So A will say that, okay, I know that what, I mean, you can apply the Dijkstra. So A will get to know that from this source, if A is a source, then what are the nodes that you can reach? Okay, you can reach to B in maybe cost of 4, right? And you can reach to maybe E in the cost of 5. I mean, you need to apply the Dijkstra, and then A will say that, okay, I can, after applying the Dijkstra, as source node as A, then I can compute the vector that, okay, I can reach in how many steps at each other router, right? That's what you can do. I hope you understood. So basically that's very easy. You can apply the Dijkstra algorithm at every node as a source. Yes, each node apply the Dijkstra, each node. Okay. Yeah, single source path. At every node you will get to you need to apply the Dijkstra, and then you will be getting the final vector at the every node. Okay. So that's all. I mean, in linked state routing protocol, there is no question apart from this. I mean, that's the only question. But there are one or two more fields that we have, which are called sequence number and age. So apart from these two values, you have two more values, which are sequence number and age. Why these two values are important? Let's just see why sequence number is important. Okay. So what may happen that you are sending your packet, maybe you are here, okay, and what may happen that this is sending the packet which is maybe like this. Okay, it is saying that, okay, this is my link state packet, and then okay, let's suppose this is also connected. Then let's suppose that what is happening that let's suppose that this path is going to take too much of time, which means, let's suppose, okay, so let me consider like this. So let's suppose that this path, okay, this path is going to take too much of time. So you send something that will reach after, let's suppose, 2 hours. But if you're sending by the path, since you're flooding in every direction, you will also send by this path. Then let's suppose it is just reaching in half an hour or maybe 1 hour. Okay, I mean it is reaching quite early. Let's suppose it is reaching in 1 minute. Now after 1 minute, it will be getting two vectors. Okay, sorry, after 1 minute, it will be getting just one vector, and then it will be basically working with this vector only. Okay, and next 1 minute, it will be getting vector from this line. Then after 2 hours, it will be getting two vectors probably, or maybe just this vector. Okay, which is saying that I mean this is some old vector that you will be receiving. Then in this 2 hours, maybe there is some topology change that might have happened, right? So basically, what may so happen if you're sending something, then this is some old vector that may reside in the network, right? Old linked state packet that is in the network, and then it may reach slowly, and after 2-3 days it will reach. And then since it is containing very old information, then this router will let's suppose this router will consider this as a new information, because this router doesn't know that it is very old information, right? I mean, maybe just half an hour ago. I mean, in this networking, it is just taking the fraction of a second. So because the bits are traveling with the speed of light. So anyway, like let's suppose that it is half an hour old information, which is very old information. So still this router will accept this information and will change. I mean, it's the routing distances based on this, and it should not happen. So that's why we have something called sequence number. Okay, so there is field called sequence number. So every packet will be having some sequence number. Let's suppose if it is 3. Okay, so if it is 3, then it means that it is and let's suppose some is having 10, some sequence number is 10. Then I will say that this 3 and this is having 10. Then I will say this 10 is latest. If it is greater, then it is latest. I will say it is latest. Okay, so I have some way to distinguish that who is latest and who is old. So suppose that it has received from A. Okay, it has received something, then it will keep track of sequence number, that from let's suppose it is A. Okay, from A, the latest, let's suppose it has received the latest as 10. Then it will say that, okay, the latest sequence number that I have received, the latest sequence number is equal to 10. Okay, it will say the latest sequence number is 10. Now, what's the benefit of this? At later point in time, if I receive this, then I will immediately get to know, okay, this is the old one. Have you understood this? So basically, sequence number, how do we, it is basically, it is helping us to know that which linked state packet is new or which is old. How do we know the LSP is new? Using the sequence number. Use the sequence number in LSP header, generate sequence number, greater sequence number is newer. Okay, if it is greater, then it is new. Okay. Now, there is another field which is called age. Now, why this age is important? Suppose your sequence number is garbled, which means let's suppose there is some error, and because of that, okay. So let me write y age field. Suppose your sequence number, you're sending that with maybe let's suppose it is very latest, and maybe I don't know, maybe 65440. Okay, very latest. Okay, very latest LSP, because the greater the sequence number, the latest it is. Okay, very latest. But what happens that this let's suppose this is 1 followed by many zeros. Okay, 2 power 30 zeros and then 1 0, something like this. Okay, this number in binary is. Now, just because one bit of error, or some error, okay, 1 bit of error, this one gets changed to 0, and then the whole number is just 100, which is 2 power 0, 2 power 1, 2 power 2, which is just 4, right? So now, just because of just 1 bit of error, this may get changed to, this number may get changed to 65440, may get changed to 4 only, which means this is saying old, very old LSP. So basically, just because the sequence number is garbled, okay, maybe in 1 bit, 2 bit error or whatever, then your the whole idea will get changed. I mean, if it is very latest, still you are saying it is very old. So the router will not accept it. But what we want router to accept it. So yes, router will not accept it. That is okay. But isn't it a problem? Yes, it is a problem. So that is why what we will do, we will have one more field, which is age. Age will say that, okay, there is one more field, which is age. Age will say, let's suppose the age is 5. Okay. Then whenever I'm sending this packet, just like a TTL, okay, I will decrease this value to 4. And if I'm receiving here at 4, then it will say the age of this. Okay, suppose that if I'm accepting this, Okay, then I will say the age of this packet is just 4 seconds, which means after 4 seconds, I will just discard this packet. So what's going to happen? See, let me just read this. That if the router ever crashed, okay, that's okay. If the sequence number is computed is received instead of 4, okay, let's suppose instead of this, you are receiving the sequence number 4. The packet 5 through, so basically the packet 5 through all of this will be rejected. Okay, that's another case. So suppose, sorry, this if this is 4, so they've taken this example that they wanted to accept. So suppose this is 4, okay, and then this get changed to a very big number. Let's suppose this gets changed to a very big number, and which is maybe 65540. Okay, 65540. Suppose that you are sending a packet with a sequence number 4. With a sequence number 4. Now it is getting changed to 65540. Now what the router will do, since it is very latest, okay, router will think that, okay, I have just received very latest packet, very latest. Router will keep it. Now this age will say, if there is some problem, if you're keeping something, that's okay. But age will say, let's suppose age is 4. It will say you keep it, don't worry, okay, based on the sequence number you keep it, but you keep it just for the 4 seconds. This age will tell you some unit of time, just for the 4 milliseconds or 4 seconds, something like that. Right? Age will say just keep it, but only for the 4 seconds. And age is also working just like a TTL, which means whenever you're sending from here to here, you will decrement it to 4. That's also true. And also, okay, it's just a time tick. Okay, I mean you will decrement at every forward, and also you will say, okay, tick 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 4 times. If there is a tick, then you will reject it, which means that you will keep it, but just for the 4 seconds. So that if the new packet is coming, which will be having the LSP, something like that, maybe 5 or something, right? I mean, sequence number will be some 5, then it will accept it. Okay, because you are going to keep this just for the 4 seconds. After 4 seconds, you will forget that you have received something, right? And then you will accept it. But suppose if you are not forgetting it after 4 seconds, then what will happen? Can you accept this 5? The sequence number 5? Can you accept this with the sequence number 6? No, right? All of the packet 5, 6, 7, 10, like all of the packets will get wasted. So that is why I will say I can keep it, but just for the few seconds. It is having some age, which is defined by the age number. Okay. So that's what I have taken from the 10 mom. So it is saying rejected as absolute since the sequence number is this, which is very high. So the solution to the problem is age, and age is saying that each sequence number is decremented it once per second or per millisecond or anything, right? Any unit of time. When the age hits 0, the information from the router is discarded. Normally the packets come and say every 10 seconds, so the router only times out when a router is down. Okay, so anyway, age field is also decremented by the each router. It's just working just like a TTL also, and as a timer also. Have you understood this, what I want to say? Okay, so I hope you got it right. Now let's just move to the next slide. Okay, should I repeat it? See, it is very easy. What I'm saying, let's suppose the sequence number is 4. If it is getting disturbed, which is, let's suppose this is a very big number, suppose, then since it is very high number, now this is a sequence number, so router will accept it, right? Router accept it. Now next sequence number from this will be 5, and the next sequence number from this will be 6, but all of these LSP will get rejected. Why? Can you tell me? Because the router is having very latest packet. Router will think that, okay, these are some not so good packet that are coming to me, right? A smaller sequence number, yes. So that's why router will reject it, and that's not a good idea. So that's why I will be having one more field, which is age. Age will say, let's suppose if it is 5, then I will keep this packet. That's okay. Based on the sequence number, I will keep this packet, but just for only 5 seconds. After 5 seconds, I will forget that this packet even exists. So that if new is coming, then I will accept it. So age is just saying that I can keep it packet, but just for the 5 seconds, something like this. Okay. Yeah. So that is all in linked state. I mean, there is nothing new. I mean, there is nothing more in the linked state, which means it is very easy algorithm. Let me quickly repeat it. That you just need to apply the Dijkstra algorithm here. Okay, at every node you need to apply the Dijkstra. Now it is having two more fields, which is sequence number and age. And what this sequence number and age will do, like why these are important? Because sequence number is important to distinguish that which packet is new, which packet is old. But if sequence number itself get garbled, then it is a problem for me, right? I can just keep the very not useful packet with me for a long time. So that's why the sequence number itself get garbled. That's why I have the age. Age will say that you keep based on the sequence number, but just for the some time. That's all, right? Okay. So now let's just see these questions. In distance vector routing, can the count to infinity happen when the link is added to the network? So I have shown you that count to infinity happens when you are basically, let's suppose this is something like this. If this link get disconnected, if you are basically adding some link, then can it happen? No, it will not happen. Okay, because it is a good news. Let's suppose this is A, this is B, this is C. If let's suppose earlier it was not there, which means it is infinity. It is infinity. Now you are adding this. Okay, so earlier it was not there, but now you are adding this. Now immediately we will say that okay, I got some new information. So A will like B will say that okay, let me immediately change it to. B will say let me immediately change it to 1, which means this one, and then like after this it will immediately change to 1, and it will be still infinity. Now after one round of exchange only, after one round of exchange, right, then it will be 1 and it will be 2. I mean, let's suppose it is 1 1. So after just one round of exchange, it gets stabilized. So that's not a count infinity problem. Why we will count infinity if that's a good news, right? So if there's a good news, then you do not need to count infinity. Now there's a mention one advantage of linked state. Linked state converges very fast. In just one iteration, it get converged because you have the whole topology. And distance vector has a less overhead. I mean, there is no flooding, right? So smaller update traffic is less here. And here, yeah, there is no loop, and it also converts fast convergence, more robust to finally or malicious nodes, faulty or malicious nodes. Okay, because it is basically not having any count infinity problem. Okay, now let's solve this question. Count infinity problem is associated with linked state, distance vector, DNS, or TCP. So I think you know the answer, right? This is B. It is linked state. Now let's see this question. What they're saying. Consider the following statement about the linked state vector routing protocol for a large network with 500 network nodes and 4,000 links. Let's suppose this is the network. The computational overhead in linked state protocol is higher. Yes, that is true. Computational is higher because you flood everything, right? You flood not just to neighbors but to everyone. Okay, here you just flood to neighbors. In distance vector, you flood to neighbors. The distance vector protocol with split horizon also avoids the looping. Persistent means just a constant looping, right? It keeps on looping. So does it avoid with the split horizon? Tell me, can it avoid the looping problem with the split horizon? No, right? Computational overhead means like whatever you are having in the linked state. So there are too much of packets transferring. If you're only transferring to neighbors, so you're just transferring to the 3. But if you're transferring to everyone, then if there are 500 people, then you will be transferring to the 500 people. So there is since because of the flooding, the linked state is very costly. Okay. Yeah, and also you are going to run the shortest path algorithm. There in the distance vector, you just take the minimum, but here you are going to run the shortest path algorithm. So that is why it is costly. Now tell me, can distance vector avoid all the looping problem? The answer is no, right? Answer is no. This is false. Why? We have seen this in the frozen, right? So if there is if there is a 3 node stability or maybe more than 2 nodes, then it does not guarantee, cannot guarantee. Okay. So in 2 nodes it always guarantee, but in more than 2 nodes you don't know. Like you do not have any guarantee. After topology change, a linked state will converge faster than a distance vector. Yes, that is true. Because linked state always converges faster, right? Distance vector may get to count to infinity. It may converge very slow, but also if not even count to infinity, then also it can converge very slow. So that's why true, false, true. So what is the correct answer? S1 and S3 are true, and S2 is false. Yes, these are the correct answer. Okay. Okay. So now let's solve more problems. What they're saying, consider a network with 6 routers, R1 to R6, connected by a link, something like this. Okay. And then they're saying all the routers are based on the distance vector routing protocol to update their routing table. Each router starts with this routing table initialized to contain an entry for each neighbor with the weight of the respective connecting links. So each router is basically initialized something like this. R1 will get initialized with it will say to R2 I can send in 6, to R3 I can send is 3, something like this. R1 will get initialized like this. Is routing table initialized to contain an entry for each neighbor only, okay, with weight of respective connecting link. So that's how you are going to initialize. After the routing table is stabilized, how many links in the network will never be used? So what you will do, you will check that okay, how many links are never going to use, which means you will check that okay, which path R1 is using, which path R1 is using to every other node, which means you are going to check the after at the end you are going to have the shortest path, right? I mean, it is going to converge maybe slow, but at the end you are going to have the shortest path from R1 to everyone. So do you really need to do it using distance vector routing algorithm, or you can just apply the shortest, maybe the Dijkstra algorithm at R1 at R2? You just find out the shortest path from R1 to everyone. Okay, shortest path from R1 to everyone, maybe R1 to R2. You will say that okay, this is the shortest path. Okay, via what is the next node? Basically, you can find out shortest path from R1 to everyone, and then you can check that which link you are not going to use ever. Similarly, you can find the shortest path from R2 to everyone, and then you can similarly check the which link you are not going to use ever. You do not need to apply any distance vector routing algorithm. This is just an algorithm question. I mean, not a computer networks question. So basically, I mean, if you want, you can apply the distance vector, but there is no need to do all of this, right? You can just check that, okay, what is going to happen after Dijkstra at every node. So they are saying if we mark then all of these links one by one, then we can see the following links are never used. You are not going to use R1 to R2. Just apply the Dijkstra. So you will say at the Dijkstra R1 will finalize this 3, right? And then in the next iteration, it will finalize this 3 to 5. So okay, see, if R1 has to reach to R2, will it be going by a 6 or maybe by a 5? Always by a 5, right? Similarly, if R2 has to go to R1, then always by a 5. So always you are going to use these 2 links, and you are never ever going to use this 6. So that's why this 6 is never ever going to use, right? Similarly, you can apply the Dijkstra and you can find the answer. Okay, there is no need to use the distance DVR protocol here. Okay, this is the 54 question in 2010, and similarly the follow-up question is 55 question in 2010 only. Now they are saying that consider a network with this one. Suppose the weight of all unused links are changed to 2, which means if this unused link is changed to 2 and there might be some other unused link, if all of those weights are changed to 2, now again do the same thing. Is used routing. Okay, till the table stabilize. See, this is a very good thing. If they're asking anything like till the routing algorithm stabilize, then you do not need to do the DVR, right? If they just ask you to do some questions where they say that okay, in the next iteration what's going to happen, then you need to use the DVR. Otherwise they are saying stabilization, then you do not need to use the DVR, right? You here also you just change it to 2 and some other link to 2, and then you can apply the Dijkstra again. Yeah, you can apply the Dijkstra again, right? Now this is the question that has been asked in GATE 2021. This is one easy question based on the DVR. If you want, I can solve it. Otherwise, you can also solve it. This is the last question. Okay, so you can solve it as a homework, and the solution is on the next page. This is just easy question. Okay, just try it as a homework. But there is one very nice question that we have in the DVR, and that's what we have solved in our theory videos only. Okay, let me just show you. See, there was very nice question. This question, you just practice it again. Here, they have defined like what's going to happen. I think they are going to say that, okay, this link is going to change to from N2 to N3 is going to reduce from 6 to 2. Okay, reduce to 2. The moment you have this 2, then you are immediately going to update this N2 vector, N3 vector. That's what we have solved in the theory videos. And then, I mean, the pre-recorded videos. And then like you need to solve this question. Just do this question. There was only one very nice question that has been asked in 2011. Otherwise, these questions are very easy. Okay. So that is all with DVR and LSP. Now, tomorrow we will be starting a new topic. I mean, new topic in the sense, new topic for the live lectures, which is IP fragmentation. Okay. So we will be just completing IP fragmentation tomorrow, and then we will be starting maybe some questions with the ARP, ICMP, and these protocols. Now, in 2 days, we will be finishing this IP, then so that we can start TCP. Okay. And but before that, I will solve maybe some more questions, and I will just convey some few more concepts. Okay. So I think that is enough for today. We can meet tomorrow. Yeah. Thank you, everyone. It was just a short class. So thank you so much. Take care. Bye bye.